Up next is our organizer, Matthias, and he will talk about physical state and conservation laws in biological communication.
Yeah, can you hear me? All right. Physicists love to adhere to conservation laws. It's the pillars of physics. It's what we hold on to, even in crazy times of quantum mechanics and relativity theory. Einstein and Planck made very clear statements on that. So if we have a picture of something, like a nice image how things might work, a nice model, maybe even plausible or very plausible, whether it is correct and should be carried on or not depends on whether it holds up against physical laws or not. That's what is the decisive judge. And if it doesn't, we should get rid of it. And we should be very, very careful with modifications. Because Einstein also made a very clear point on that. And by the way, what I forgot to say, up there in that room, there's a whole lot of books, including Einstein's autobiographical notes, where he says exactly that. So, if we as physicists enter a new field, we first have to check whether the authors that shaped this field had their conservation laws straight, whether they had the physical laws straight. And of course we all agree that physical laws we have to hold on to. Of course, that's not what I mean. It's not mean in any arrogant, mean in any way. But it's not enough to accept that the laws hold. It needs to be in your mind when you form your model. Because physical laws, like energy conservation, is not obeyed by accident. You have to do your math correct. And if you don't have it in your mind, if you simply neglect it, I don't mean that you don't accept it, you simply neglect it, you will violate it. At least in most general cases. Well, whether a violation of a physical law is relevant for our understanding of phenomena may be a different story, but you should be aware of that. So if we as physicists enter the field of biology, we have to do simplifications. Otherwise, we can see the forest for the tree. So very often we do simplifications and we call a bird, everything's a bird. Although, of course, we know it's much more. Biology is diverse. It's what Darwin teaches us. Without variation, there is no interesting life. There is no life. That's kind of gives us physicists a panic attack almost. There's constant variation on the one hand, but we want to apply universal laws. We want to make simplifications, and simplifications might very well, for example, to find out whether a horse floats in the olive oil or something like that, but does it really explain biology? So this is a conflict, and this is something that was one of the things that ran through my head when I organized this conference, and when I talked to Jean-Pierre prior to the conference. That is, on the one hand, the things that biologists love, the beauty of diversity, which is truly there. And there is, on the other hand, the universality, the physical laws that we hold on to, and that brings success to physics, the success we have today. And those two things are somewhat in conflict, but they may not be in conflict. It's not that I say there's a necessity that they are in conflict, but at least on first sight they look in the conflict. I hope we can discuss this a little bit more in the roundtable discussion of diversity versus universal laws and where we can bring them together. With this, I want to come to the main core part of my talk, which will be connected to, of course, what I just said, how we can come from physical principles, namely from the state on the one hand, that Thomas was talking a lot about, and conservation laws, that Thomas was also more or less talking about already, and the conservation of momentum to biological communication. And as a physicist, you try to start from scratch and ask yourself the question, what is actually a cell? And how does one part of the cell know what the other part is doing? And this part, and this part, and this part, and this part. What makes it actually a unit? We talk about a cell, and cell is the basis of all life, of all living systems. But what is it actually, a cell? What makes it a unit? And just on a different scale, you might ask yourself the question, what is a multicellular organism? An organ. How does this communicate? How does the one cell know what the other does? It's a liver, even a liver, let alone a brain, is much more than just a number of cells. A powder is much more than this. So we ask ourselves these questions. And the question is now, so yes, you might understand the individual components here. Like in an orchestra, you might know you have a good violin player, or you have 2 or 3 good violin players, but this is not how you get a symphony. You're putting them just together and you still get a mess. You're not going to get a nice symphony. It takes more. It takes more to understand just the enzymes of a cell to really understand how it communicates. At least that's what I believe. And then we physicists, when we enter the field, we have to deal with biochemical pathways. And if this is the solution, if this is really the only solution, I give up. I admit, I will give up. But I don't believe that this is the only solution. I don't think that's all. I don't doubt that the chemistry is going on, don't get me wrong. But also chemistry is subject to physics. Of course they change with pH and they were in thermodynamics. And, lots of our fathers, scientific sense, talked a lot about physical chemistry and the role of thermodynamics in chemistry, and can barely be underestimated, of course. So what I want to present here, a little bit of different look that is very closely related to what Thomas and Connie is working on, a physical approach to these things. So let me talk about this a little bit. Well, if you want to do communication from a physics perspective, what does physics offer as a mechanism for communication? Well, on the one hand, there's diffusion. I think this is widely accepted, that at least in the sense of diffusion of particles, that this is a way of getting communication from one point to another is fairly clear. What is quite new, maybe not anymore, since the talks of Thomas right now, is how about sound? Of course there is sound. And I want to make the point clear here, because we have, we talk a lot about with our referees of our papers. It is not at all weird to talk about sound as an idea for communication. It's the natural thing to talk about. Because if you want to talk about how we communicate, we say, and we communicate through a media, through a continuum, you have to assume momentum conservation, which eventually, combined with thermodynamics, leads to sound. It's as simple as it is. Not considering sound, to come back to my first slide, means you do not have momentum conservation in your mind. It's a native, natural way of thinking about these things. So this is kind of an important statement for me to make. Let's dive into the meat. Josef Griesbauer, one of my PhD students, did the following simple experiment. A lipid monolayer, air-water interface, half a membrane if you want to say, and he tickled the membrane by different means. Tickling means putting chemicals on it. Later on, then we'll talk more about this. Shamit did it mechanically, we did it electrically, we did it optically, all kinds, or chemically even with pH. Bernhard Fichtel did that. So in many different ways we tickle the monolayer. And within the monolayer you have 2 pressure sensors that can pick up whether there is a propagating pulse or not. So indeed, if you tickle the membrane, you see, if you measure here the lateral pulse, these are the 2 traces of the first pressure sensor and the second pressure sensor as a function of time, you see that the lateral pressure is going up and down. Now, because the beauty of the lipid monolayer, you can simply compress the monolayer, you can change the state, the thermodynamic state, which means you change the compressibility, what you see here in red. You can make the membrane soft, you can make the membrane hard. Hard is low, soft is high, and you can measure while you do that the sound velocity, or the velocity of propagation. And what you see that this velocity follows an inverse square root in compressibility, what we expect from sound as Thomas just described it. So yes, we can conclude from this already, 2-dimensional pressure pulses exist in membrane, and they propagate with very little change in amplitude, so quite with very little dissipation. The velocities, and I'll come back to this later a little bit, are 0.1 meter to 1 meter per second. I want to make another point important here. So also all these things, I just will not keep hopefully repeating myself also this relates to Thomas' work very much, that the pulse is not a mechanical phenomenon, not just a mechanical phenomenon, but it's an everything pulse. What that means is the membrane, of course, is charged or has a dielectric constant. So if this is compressed and expanded, of course the electric fields around it are going to change. The charge density is going to change if there's a compressional wave. And if the charge density changes, ions will be sucked in or pushed out. You know, if the compression takes place during a sound pulse, the charge density might increase here, and protons or calcium or whatnot is going to be attracted. And when it's relaxed, then it goes back down. So with the propagation of the mechanical part, you have a propagation of an electrical component, and you have a propagation of ions, of the chemistry, if you want. And we could measure that. We could measure pressure, besides the pressure pulse, we could measure an electrical propagating pulse and a pH pulse. And this will come back to us when we talk about enzymes. So I call this an everything pulse, based on momentum conservation and the laws of thermodynamics. So I don't explain this because this is what Thomas just went through, the couplings that are measured on action potentials between temperature and forces. But what we see in the monolayer is they have all those mechanical, electrical, and thermal components that mainly, or to a big extent, Sasaki has measured. They propagate in the order of 0.5 meters per second. That's what you know from unlinear nerves, quite common velocity. You know, of course, nerve pulses are not just 100 meters per second. So action potentials are all over the place. You know, even in nerves, but if you go through action potentials in general, you have 5 or 6 orders of magnitude in velocity. So any theory that focuses on just one velocity has to be very careful. But I think we know to discuss and how to deal with that. Anyways, but this would be cheap to say that this already proves that action potential is a mechanical pulse, because there are some funky features. Thomas was just mentioning them, and they don't seem to be so obvious in sound. So nervous impulses show a threshold, or people call it an all or none behavior. I'm not particularly, it's not very important to me how we call that. It shows saturation, means if you increase the stimulus, eventually the amplitude reaches a maximum, it doesn't increase much further. All those things have to take with a grain of salt, though, if you look in the literature. And they annihilate under collision. So two action potentials annihilate. Of course, this is not something that's very intuitive for sound. If you talk and I talk, we might not understand each other because there's too much talking going on, but the sound doesn't disappear. So, can we actually explain those things based on acoustics or based on sound? And just like Thomas introduced, yes, you can if you go nonlinear. So we have the linear regime, this is what I just described. We have the excitation strength versus the pulse amplitude, and it's more or less a linear relation. And then Shamit, who is here as well, a PhD student in Boston, came into the lab and was sent on the mission to go for the nonlinear behavior. And so what he did in stimulating the pulse close to a transition, to bring the monolayer close to a transition, right around here, and you stimulate it there. And you stimulate it when you vary the stimulation. And what you see is just like this sigmoidal or this threshold type behavior in excitation strength versus the pulse amplitude of the propagating pulse. And here is the corresponding pulse. You see, if you increase the stimulus, not much happens. It's actually just a linear increase that's very minor here. And then if you go over a certain value, all of a sudden the pulse is there. If you are near the transition, it behaves quite solitary, meaning like it keeps its shape over distance and things like that. And if you send two such monolayer pulses against each other, this was the work also from Shabin and another PhD student here of mine and Kevin, they actually partially annihilate. So we have two pulses here, one sends from the left, one from the right, and what you see here, the dotted red line, is the simple mathematical superposition of the two pulses. If you could just add them up, what should come out? But what comes out is the black curve. So the part that is marked here is what's kind of missing in the experiment compared to the simple linear superposition. So I could say, yes, even the funky behavior of the action potential can be easily explained and experimentally. experimentally shown and proved with nonlinear sound, which makes me quite comfortable to keep on going. Let me give a little bit of note on the velocity of propagation. So if you add the entire, if you do the elastic behavior, you saw it already. That's what we started with too. You get 100 meters per second if you plug in the compressibility and the density of lipids, roughly. However, what we have done, we have accounted for the viscous coupling. It's actually was inspired by Landau, who had a nice little chapter in his book of hydrodynamics where he has a vibrating blade. And it says you have to account for the fact that the adhered water, of course, that you have a boundary condition, the adhered water needs to swing along. So just like if you have a compression and expansion in a sound, there's a certain, almost like an evanescent sound field in the liquid as well. And so the sound pulse is going to drag, in terms of motion, some water along. But you can, one way of the interpretation would be that there's more mass that has to be moved if you consider viscous coupling, from which you actually can derive a dispersion relation. So the higher the frequency, the higher the velocity. So you could actually have a physical reasoning for your dispersion relation that might actually fit quite well. So if you plug that in, if you include this coupling, you get something that is called a penetration test. This is actually terminology I take from Landau. It means how far does this perturbation of the sound wave reach into the bulk. And you find that the new velocity, the velocity including viscous coupling, is the thickness of the layer, the membrane, divided by this penetration test times the elastic velocity. And this term is very straightforwardly defined by the physical properties of the surrounding media, namely the density of the viscosity of water in this case, the density, the frequency of the wave. You can measure all those straightforwardly. If you plug that in, this is roughly a factor of 1,000, so you get velocities of 0.1 meters per second, and this is what we see in the monolayer. This is the order of magnitude. So you get a factor of 1,000, so it's a quite significant change. And let me compare this with at least. Oh, sorry, one more. Yeah, basically in another experiment, what we have done is you try to cut off the bulk by placing the lipid monolayer on a solid. So now you don't have a bulk.
May I ask this?
Yes.
This viscosity, does it add dissipation in there? Do we get heat dissipation in that?
You should get some dissipation in that, yeah, but we didn't calculate it. But we should get some dissipation, but we see in the experiment the amplitude is not decaying much over long distance.
Yeah, it depends on
But you should,
how much it is.
but yes, it should create some dissipation. Yes, it should create some dissipation. So what we've done in another experiment, we put the lipid monolayer on a solid, so there's now just a little bit hydration layer for Vera. There's just a little bit hydration layer there, and not much bulk. So not a millimeter of water underneath. And if you do this, you recover the 100 meters per second. So if you cut the bulk off of the monolayer, you get the 100 meters per second. If you include the bulk, you need to include the coupling of the viscous charge. But this seems to be at least quite consistent. And at least I haven't found too much, maybe some of you know more, but there is a nice paper on Luzzati, Mr. Membrane X-ray, so this is who measured the two-dimensional elasticity of a nerve by X-ray, the factorial nerve. It was alive, so he checked electrophysiology before and after the experiment, and he gets a two-dimensional elastic constant of 0.2 Newton per meter. This is pretty much what you expect from a lipid layer. It's what he concludes actually from that too. That it's the lipid layer that makes the compressibility, or the compression almost. If you plug that in the sound velocity, you get 300 meters per second. If you account for viscous coupling, as I just introduced, you get 0.3 meters per second, roughly a factor of 1,000. And you measure 0.3 meters per second. So if you measure the velocity of the old pipe or factorial nerve at 12 degrees Celsius, you get 0.3 meters per second. So I believe at least we cannot simply neglect viscosity. As annoying as it might be, because elastic theories are, of course, much more elegant. Finally, I want to point out one more work on viscosity from Kukita. If you can also calculate how the velocity should change with viscosity, and what we find is that it should scale with 1 over the square root of viscosity. And at least I admit this has to be taken with a grain of salt. They only have 5 data points here. So they changed the viscosity from, I think, from water to 3 times water. So it's 4 or 5 data points. But they find the square root scaling of the action potential propagation in the squid as a function of the media viscosity, just like the scaling that we find. So at least it supports to me the idea that we need to think about the coupling on the media, and this might also be very interesting when you think about what the myelin sheet is actually doing. Myelin sheet might not be just make the membrane thicker, but it might actually separate the actual core of excitation from the bulk. Okay, that's all I said. So I want to give you a little intermediate summary, because this was my first part, based on that we cannot forget momentum conservation and how we try to experimentally support most of Thomas's theory in the modular experiments. So I want to conclude that interfacial sound pulses are predicted from momentum conservation in thermodynamics and are confirmed. And they have all features, at least microscopic features that I know of, that action potential have as well. The debate on microscopic phenomena that take place there, of course, remains open. I have no new contribution there at the moment. But we will talk about this in the round table. A prediction that I think we agree on, that we all make, more or less, is that during an action potential, the system should go through a transition. And this should be experimentally confirmed, and we have to confirm that. So I take it, the ball is in our field. We show that there is a phase transition actually taking place. The reaction potential propagation, and Simon Pavionka, a PhD student in our lab, will talk about where we stand on this tomorrow. Actually try to do this. I want to change the pace a little bit and talk about now another idea, and I will come up in the last part and I'm combining those two ideas. This idea is the idea from state to function, which again you have seen already in many respects in Thomas's talk. I want to, because I'm probably not going to be capable to convince you, but I want to let Einstein speak, and again the book this is taken from is over there in the room, and really I can show you the parts, where he talks about what a good theory actually is in his autobiographical notes. It's not the young Einstein, this is the wise and old Einstein. Maybe he was always wise. A theory is the more impressive, the greater the simplicity of its premises. The more different kinds of things it relates, and the more extended its area of applicability. Therefore, the deep impression that classical thermodynamics made upon me. It is the only physical theory of universal content concerning which I am convinced that, within the framework of applicability of its basic concepts, it will never be overthrown. Never be overthrown. So I don't think he said that about anything else. So he was a big admirer of thermodynamics, and so am I. A very important approach, a very important part of his approach, is what later on Schrödinger or Sommerfeld called Einstein's reversion. So he talks about the cornerstone of thermodynamics, which is not necessarily the first law, but it's the second law. The second law is the fascinating part of thermodynamics, really. And the relation between probability and entropy from Boltzmann. And he talks about this formula here. In order to be calculating the probability, one needs a complete theory, perhaps a complete molecular mechanic theory. All MD simulation. We should talk about this, of the system under consideration. Given this kind of approach, it therefore seems questionable whether Boltzmann's principle by itself has any meaning whatsoever. In my words, I would say what he says is that it is hopeless to have a complete molecular theory of the system. So it's meaningless to start from a molecular theory of the system and calculate the probability, and calculate from the probability the entropy. Because this is how it was taught to many of us who listen to statistical mechanics during their physics courses. But he has a solution of the problem. He does not leave it like that, has no meaning whatsoever. He completely agreed on this formula. It was not the formula was not the problem, but the approach. And he said we can proceed reverse direction, hence Einstein's reversion. From the empirical a certain thermal behavior of the system. And this is, for example, a mechanical property. This is an empirical term of a certain behavior. This is the black body radiation was the first time he applied the empirical term of a certain behavior. A heat capacity, as Thomas has mentioned, is a conductivity, electric capacity. This is the empirical term of a certain behavior. It's empirical, it's a fact. It's a fact, it's not a model. You measure it. You can do stupid measurements, but it's not a model. It's not a model assumption that can be tested. One determines the entropy values of the individual states, and from these one calculates the probabilities of the system by means of Boltzmann. It puts you in the advantageous position that there is no elementary theory necessary. So if you want to bypass needing molecular models and interactions, you use Einstein's approach. In long story short, don't start from molecular models, start from state diagrams. This is what Einstein proposes, and I follow, because I guess many others follow this idea. It's beauty, but it doesn't satisfy our need of thinking about molecules. I agree. So this is something people have to debate on, but there's no question about it that this was the great success of Einstein's applying thermodynamics. If we do so, if we apply this reversed version, first the state and then the function, let's say a membrane fluctuates, can fluctuate, has to fluctuate. It has to fluctuate. It's a consequence of the second law that a membrane stands still. It has to fluctuate. And as Nagel, Scott, and Connie and Wolfgang Hanke posted there already pointed out a long time ago, the fluctuations are high with compressibility, and this may introduce the idea, well, let's say if fluctuations are high, the chances for a pore to open and an ion passing through is increasing. So the interpretation is very simple. This is straightforward thermodynamics, and then you throw in your interpretation for a biological function, because biological function is not, that's something that's subjective, right? That's something we need to agree on, whether we call it a function. We did the experiments. Wolfgang Hanke is much better at this, and he will talk about this, so I've skipped this with black lipid membranes. Many others have done this. Of course, Antonov in the 80s already, Wolfgang Hanke, Connie, Thomas, one of Thomas' students, Heiko Seeger, has done very nice experiments with including proteins, but this is a protein-free system. So you expect a lot of fluctuations if the system is soft. You don't expect so much fluctuation if the system is hard. So you expect high conductivity if the system is soft. You expect low conductivity if the system is hard. You relate state with function. And if you do the math, do the experiments, it's exactly what you find. Here you have the conductivity in red, and here you have the compressibility in black. So it's exactly what exactly how Einstein proposes, what we have done here, and from this approach we're following that fluctuations can trigger conductivity. And I want to just say, we have to address this at some point, that the fluctuations that you find in pure membrane system look just like the ones that we count ion channels for in cells. And we cannot just simply wash this away with something, yeah, but nature hasn't used it. This is too simple. This is a control experiment if you want. If you want to prove that an ion goes through a protein, you need to do the control experiment, which is take the protein out and see if the phenomena is still there. And the phenomena is still there. And this cannot simply neglect it as an artifact, or yes, we know this. I mean, I heard all kinds of funky comments. People don't disagree. I think Wolfgang knows exactly that he saw it a million times in his life, and so did the students of Thomas. You cannot just neglect this. We'll have to discuss this tonight at the round table or some other point. But a completely different way, maybe more interesting for the people from the biological community, is how to apply the state to function relation with catalysis. And this was inspired by a theory of Connie, and was a great collaboration with Israel Silman, who's very happy that he is here. He provided us the enzyme, and what we have done here, and those two students, Stefan and Bernhard, they incorporated the enzyme from Silly into a lipid monolayer, and we simultaneously measure activity and state. So we have an Ellman assay, for those who are familiar with acetylcholine esterase. This is the enzyme we started with. We have an Ellman assay, and we measure activity and state simultaneously. And what you see is that. Is here already. The black curve is the compressibility, the red curve is the activity. So it's not a simple Arrhenius plot that, you increase the pressure, you decrease the activity. You have parts that this is true, and you have parts that this is off. So it's not that simple. But what actually correlates, again, is the state or the fluctuations and the activity. Just like the conductivity state related. So you can conclude the state, or as a representative of the state, the compressibility, is proportional to activity and conductivity. So these things, activity and conductivity, have to be considered in a thermodynamic context as well. Now, if you put those two things together, first idea talking about pulses, second idea talking about state changes, what we have done is you include an enzyme into a membrane and you excite a pulse. And we do not do it here like biology properly does it by incorporating having another protein there, but we actually tickle the membrane. And we had the same setup that I showed before. We had the enzyme in there, and when the pulse propagates across the enzyme, it's not a single molecule experiment, about the area where we measure the activity of the enzymes. When the pulse propagates there, you see here, the activity of the enzyme shoots up by a factor of, depending on the experiment, at least an order of magnitude, sometimes more. So the pulse triggers an activity change in the enzyme reversibly. When the pulse is gone, the activity goes back down to baseline. So this pulse can communicate with the enzyme if you want. The enzyme can hear the pulse and work it differently. But now you want to, of course, usually the question is, shouldn't you have these pulses there all the time? You know, you're breathing in, we're jumping around, we're having our blood pressure, we're having chemistry and temperature changes going on in our body. So the system is continuously under attack, under little small free energies attack, if you want to use Thomas's terminology. So is there anything specific about it? Or is it just a whole bunch of pulses and a whole bunch of variations in enzymes, and biology has to see how they form life out of this mess? I want to convince you that it can be specific. Very simple idea. Imagine the enzyme sits in a state far away from the transition, and the pulse propagates. The pulse is reflected here by the little blue line. So it won't do much if the enzyme is far away. If the enzyme is closer to the phase transition, or the surrounding of the enzyme, the membrane is closer to a transition, and the pulse arrives, it will kick the system within the transition, and activity will kick up. And if the enzyme is already near a state of transition, is already optimized, so to say, and any pulse will depress activity. So the pulse-enzyme interaction becomes specific already through the thermodynamic state of the membrane. But there is more to it, because enzymes have also a pH optimum. And I told you in the very first part of my talk that pressure pulses also include pH pulses. And that's why it's extremely important to not just simply say this is a mechanical phenomenon. It's much more than that. All those things are coupled. So along with the pressure pulse, there's a pH pulse. So the local pH will change. And only if the change in pH brings the enzyme closer to its pH optimum, and I think most enzymes have that, then it will increase the activity. If it brings the enzyme away from its pH optimum, it will decrease the activity. So imagine a pulse propagates, these two enzymes have different pH optimi. This one will be activated and this one won't. And now you have two things acting together. Only if the state of the membrane and the pH optimum both are fitting, you get a large increase in activity. And it's still not enough. You have also specificity on the trigger side. So the center. So if you want, this is the receiving end, this is the sending end. Because significant pulses will only arise, let's imagine you have an enzyme sitting here, the substrate comes in, some local pH change, just to give you an example. That if the local pH change is as such that it kicks the membrane through the PK, it will trigger a pulse. If it only mildly changes the state of the membrane, it will not trigger a pulse. You need a significant bang to get a strong pulse. And if the pH change of the enzyme kick the membrane through a PK, to a protonation transition, it will condense the membrane and send out a pulse. So you have the PK of this sending side, you have the transition of the membrane, and you have the pH optimum of the enzyme. You have three transitions, and only if all three take place at the same time, you get optimum increase in activity. And this is highly specific. So these two guys, this protein and this protein, they interact very specifically. They have a very specific interaction. And I can map this in a phase diagram, and we will see a beautiful talk of Wilson Philippa, where he maps many more such things into a nice phase diagram. So you imagine your state is here. all those noise of these little free energies that bombarding your membrane. Every now and then you get a significant state change, but only if the state change is such that you land right into a transition regime, you're gonna get an increase in activity. So specificity comes in because phase transitions are specific, not because of lock and key matching. And so this is my idea of specificity, and with this I want to summarize. I tried to pitch you 3 ideas from state to function, which was actually the second part, so that we should discuss how we include thermodynamics if we want to talk about molecules, how this fits and how it doesn't fit. It's not trivial. It's not a yes and no question. Answer. The communication follows from momentum conservation, and momentum conservation is mostly neglected, at least in the most common biological textbooks. Maybe because it may not be the fault of the biologist, because of physicists being afraid to enter the field. So it's not, don't take it personal. And tier 3 was that I wanted to give you an idea of a concept, how you get specificity from physics. Lock and key is not the only way of how something can be specific. I'm not excluding lock and key, just saying it's not the only way of how things can become specific. So we want to do more of this, going towards multicellular life, and now you have pulses propagating over the system, and this might be very close to, or at least related to what Jean-Pierre thinks about. You have pulses coming into your system, they change the chemistry will change the synapses or the connectivity, and you have a feedback mechanism between pulses and biochemistry, so these networks can change under the presence of pulses. And this is where we want to go and understand multicellular life. And with this I want to thank you for your attendance, and what I'm specifically saying, Connie was always a great inspiration for me, and all those things we have done was somehow traced back to him. And I also want to specifically thank Christian Villa, for it was a real blessing that he came to me in 2011 in Boston and remained staying with me. And I want to thank my family and you for your attention. Thank you very much.
Thank you, Matthias. We have time for questions.
I'd like to come back to your first part where you talked about the viscosity and Schwann cells. You need only a thin layer to really disconnect the bulk from your nerve?
Do you need
a thin layer to disconnect the nerve from the bulk? Or how is the thickness of the myelin sheath playing into that? Can you comment on that part?
I would think it should be somewhat related. I think it needs to be fairly thick. Usually, my gut feeling, I have not done the math, but my gut feeling would be that it should be something in the order of the wavelengths of the exponential, so that the way the wave spreads into the bulk is somehow related to the wavelengths of the meters. Yeah, or millimeters if it's fast.
Because if you think about it, there's a correlation in terms of conducting velocity and thickness of the myelin sheath and the nerves. So I'm wondering how that plays.
I mean, it's hard to answer like that. I mean, it depends. From the theoretical part, you want to make sure that the viscous coupling is taken care of. How you do this precisely would need to go into the physics of the myelin sheath.
If you think about this way, I always thought you only want to have the viscous coupling way. You only would need a thin sheath, right?
Mm-hmm.
So why then the correlation in terms of velocity?
It doesn't have to be so simple. I mean, the myelin sheath is material. It's not the perfect solid. So you can have some kind of... Yeah, but sure. But there is some kind of elastic response which makes some part to dissipate, another part to remain within the elastic. So different radii of the Schwann cell will result in different dispersive effect on the person. Like I said, you have to go a bit into the details of
in the ideal case, you're right. In the ideal case, you're right. If you make something really close, like a really completely rigid rod around the nerve, that's really sitting on the nerve, but doesn't somehow influence it, which we have to think about now. You have this, C component of the nerve pulse. But then it's true. Then the thickness really actually shouldn't matter. But if the sheet is soft and has a viscosity itself and has elasticity itself, it gets a little bit more tricky. But I have not done the math. But I understand that the layer of the myelin sheet can vary quite a bit also, right? There's not one number out there. There's quite an order of magnitude. So yes.
Beautiful. How do you deal with the nœud de Ranvier? You know, because you have a propagation of nerve impulse, which is not continuous on the nerve membrane, but jump from one nœud de Ranvier to the other nœud de Ranvier.
Saltatory, what they call. Yeah, I mean, if the pulse gets really very fast, I mean, it looks like a jump. But do you really know?
Do you believe that there is a physical propagation below the myelin sheet?
I do. Yes, that's what I do. This would be a prediction. Yes.
You have evidence for that?
Do I have?
Evidence. Physical evidence.
No. This is a
May I
prediction.
say something
Yes, of
about
course. But this would be a prediction. Not a. I don't have to prove for this.
I think
Now there is another point. Just what do you call physics? And because in one hand you compare the properties of a solid, which is elastic properties or whatever, and on the other hand you compare that with a system, which is a biological system, which is not homogeneous.
Which is not?
Homogeneous. In fact, the physicists had so-called, because I don't make any category of this kind. I think this is the institution or the history which has cleaved physicists from the biologists, whatever it is. But what I usually call physicists, or what they call themselves, are in fact working with systems which are much more homogeneous than the biological system, which are in fact highly heterogeneous.
Yes.
And that's the reason why I don't think I am going to disagree with what you said.
But I think there's a challenge behind that.
There is an enormous difference there. And in the sense that you may have an internal granularity of the biological systems which may itself be explained by physical laws within each of the components, and of course I'm talking about the proteins. And in his view, you eliminate the proteins.
I want to think about them differently.
Don't care, but we can discuss that.
Yeah.
And I think this is something which I wanted to say. We can continue the discussion, of course. There is a discussion on that.
Yes,
today.
absolutely.
Okay, but my last point is, why don't you work on systems which are more homogeneous than the membrane, and where there are chemoelastic properties or chemomechanical properties, which are the contractile fibers of the muscle. And there you may have a system which is closer to what you call a physical system, so to use this word. And there you may really follow a wave of propagation of which could be analogous to really a sound wave, in the sense that it is the conformation of the protein which is propagating all along the muscle fiber. But why don't you use that?
Oh, absolutely. That's why we invite people like you. because I personally don't really. It doesn't matter so much for me what I am applying it to. I just want to see does biology make use of this sound propagation, and I have not really any contradiction with what you say. I think that this feeling of diversity and heterogeneity.
More relevant to have it in such a system where you know all.
Absolutely, yeah, absolutely. No, this is, I don't need to start at the most complicated system with this respect, yeah. And the heterogeneity is, that's what I mean by the original diversity. You know, this is a challenge, you know. Obviously a bird is more than just a bird.
There is a historical point. I want to make. When you put mechanics in the picture, then everybody has learned about, and the textbooks are quite okay. So it looks okay for us to have a mechanical picture. When you enter entropy, you will lose most of the audience, because the textbook authors today have not understood entropy. They have to go to language or to that. There are some who have understood, and it's a big thing. I will focus on that. So if we now come to your question, I just to give an example of how I explain experiment, and there are experiments in contrast to what you say on the movement in the violin sheet, and the experiments are by Tasaki, very, very old. That in the violin sheet you have a nervous impulse, but it's 100 times smaller. It's very little with the electrode to see, and in the Dortmund node. And my interpretation is straightforward, but not really fully experimentally checked. I just say, okay, 2 dimensions, we have what Shamit sees, what you see, and that's it, and the Hodgkin-Huxley I don't touch. But the moment the things become not 2-dimensional, I say 2-dimensional because the phase diagrams are 2-dimensional, Langmuir-Trost. No? It's a 2-dimensional, but they become a 3-dimensional. Something happens, which also happens in pure water. If you throw a stone in the river on one side, the fish will hear it first. The sound arrives with a kilobit per second. The water wave at the surface is 1,000 times slower, just as a violin tour. So you have the same sound wave. It gets to 3 dimensions. The electrical signal is much more little because you have a symmetrization by this symmetric and so on.
So I don't think you can make the call. Of course, there are 2 options. What Connie basically proposes, the one thing is that if a thing gets from 2-dimensional to 3-dimensional, the E modulus gets up and things get faster. This is one way to think about the thing, but to neglect the viscosity would be a very bad mistake to do. And so I wouldn't make the call whether it's the viscous coupling or whether it's the elastic changes. Because keep in mind, you need to explain a lot of velocity changes. If you go from 0.1 meters to 100 meters per second, 3 orders of magnitude in velocity, that's 6 in elasticity, and that's a tough nugget. That's a tough nugget. You need to convince me of that this takes place 1,000,000 times harder. That seems to be.
Are there any
not
other,
easy.
sorry, are there any other questions? We have time for one more.
Very short question. You mentioned this point that it would be useful to measure the change of state during the actual potential. Didn't anyone measure that up to now? Because it's technically so trivial.
I don't have any really good experiments that people would try this with Raman, and there are some hints, but I don't know if I for myself, if I put so much money on this phenomena, I want to have very clear experiments, and I don't see them as clear as they should be. Why people didn't do that, I don't really know. I don't know. I don't know much that has been done. We trying it. We are trying it since a while. What's that? A phase transition in a lipid bilayer?
Looked at fluorescence and also at isotopy, I think, didn't he?
Yeah, that Tasaki has done that. Fluorescent electrons.
Yeah, but can you conclude from?
Phase and Larry Cohen.
But can you conclude that there's a phase transition from this?
There's a conformational change.
Well, okay, you have changes in voltage, right? Anyways, that's the Hodgkin-Huxley school, and this can change the dye intensity. But I think what I've already convinced that it's not the voltage change that changes the dye, but
I think that's a tough question, right? If you measure a transition, everything that changes in a transition has been measured in a nerve pulse.
Yes, it is a tough.
So that means every measure that you would have for a transition actually does change in the nerve pulse. So in some sense, it has been proven.
Just to say one word about the conformation change during the action potential. I think the sodium channel both has been crystallized, and the elastic transition of the sodium channel are being explored by Bill Cattrall in Louisiana. So there is some evidence that whether it agree with what you say or not, but it is a fact that there is a conformal exchange of the sodium channel which can be followed and measured, and it has, to my opinion, been measured. I don't know to what detail, but I know that there are, at least for ligand-gated ion channels, these kind of genes have been identified, and now there is a whole field where physicists or chemists, whatever you call them, are very attracted by is the molecular dynamics of what's happening to this protein.
Yeah, well, no doubt confirmation change on there. Yeah, no doubt.
Okay, so I think
I'm going to stay around.
Do you have one comment?
So if you believe that the retina model, the waving retina, is a 2D model, like the actual protection is in the axon, then TTX is gone because there is
And what you want?
TTX, the tetrodotoxin.
Yes.
We know that does nothing at all in our wave, so it's out there. So it is, I think that is should be a positive to our side.
Excellent. So you are going to talk more about this in your talk?
Yes.
Yes. Okay, then I'm not going to ask you now.
Okay, so I think there are several more questions, but I think we discussed at the coffee break now. Matthias will be around and we'll be having a roundtable tonight and tomorrow.